So here's an outline of the talk. I'm going to argue that what's happening right now on planet Earth in our lifetime are things that are significant in the history of the planet. It's existed for over 4.5 billion years. But you cannot see that clearly unless you understand not just the history of humanity, but the history of planet Earth, and also how all of this fits into the history of the universe. And that's why I believe it's absolutely crucial that we all come to understand a modern science-based origin story, and that we teach it in schools to the young people who will be managing planet Earth within the next few generations. So here's a brief outline of the talk. I'm going to talk about why I think of this as an origin story and what I mean by an origin story. I'll try and explain that. And then I'm going to try to give an outline of the story. Now, that basically means I'm going to try to give you a sort of 15-minute history of the entire universe. It can be done, sort of. But I'll try and do it in such a way that shows why it's really important that we understand this history in order to understand the moment we're living at. So the third part of the talk will be about the place of us humans in this story. And I'm going to argue that we humans are a very big deal in the history of planet Earth in a very precise way that I'll try and explain. And I'll end up by talking about big history, about this sort of emerging discipline that tries to put everything together and where it is at the moment. So that's an outline of the talk. So let me start with the idea of an origin story. What do I mean by origin stories? Well, as far as we know, all human societies have taught what I call origin stories. If you look at all the great religious traditions, at their heart is a sort of cosmology. It's a story that puts everything together. And it's true also of indigenous traditions where there was no writing. I come from Australia, so this is very important in understanding Australian traditions, and it was probably true of Paleolithic societies throughout human history, that at their core there was an attempt to put everything together, to put together the best knowledge that that society had of its world, and to put it together in a form that was engaging, that was interesting, and that was accessible to young people. So origin stories seem to have always lain at the heart of education. They provide, one way of describing it is to say a sort of universal mapping so that you can place yourself in something larger than yourself. One of the big problems about today, I think, is we don't provide that sort of mapping within modern science. And that leaves us with a sense of not knowing quite what we are, what it is that we're part of. So origin stories are absolutely crucial to one's sense of identity, and I'll try and illustrate that in a minute. But modern schools don't teach a modern origin story. They still very often teach the old origin stories, but lurking within modern science there is also an origin story. And what I've been trying to do for years is to tease out that story and to tell it in ways that are as engaging as traditional origin stories. And origin stories, so what they do is they try to teach how everything fits together, and the failure to teach origin stories today means that many young people don't know how all the bits and pieces of knowledge fit together. They can find an immense amount on Google. What they can't find is how it all fits together. Now, let me give you a sense of what I mean by mapping of the self. This is something origin stories do, and this is a very crude graphic that tries to show this mapping process. So we all have a sense of self, or our identity as self. We have a sense of ourselves as embedded within a family or a very small community of just a small number of people. Then beyond that, there may be a sense of a village or a clan or an institution or a workplace. So these are all different identities that are embedded within each other. Then beyond that, there's the national identity. Now, in today's world, that's immensely important, and it's important because governments insist on teaching it. They want young people to grow up as loyal to that particular government. Now, I have to say that in a world with nuclear weapons, I think to carry on putting nationalism at the center of our education is completely crazy. In a world where conflict between nations can lead to complete Armageddon. But that's an identity we understand very well because it's very well taught. The next one, humanity, is barely taught at all. If you ask, where in the world can you do a course on the history of humanity? Can you do a course that'll give you a sense of the history of humanity that is as inspiring, as engaging as the histories of nations that we see today? The work has not been done in putting it together, and we don't teach it. And I think for the reason that governments have little interest in teaching such courses. Then next, there's our identity as members not just of humanity, but of the biosphere. We share this planet with billions of other species. They're our kin genetically. We're related to them. We evolved out of the biosphere. So that's another community that we're part of, the biosphere. And then beyond that, there's the entire universe. We belong to a universe. And our lives are shaped by that universe. So that's sort of what I mean by mapping. But there's a second sort of mapping. If you do that mapping, you have to link disciplines. You cannot educate people by treating history as separate from economics, as separate from physics. So let's go back to that identity I've just shown. We begin with ourselves. Let's say psychology can teach you something about what it means to be a self, to be a person. Sociology talks about people in groups. Anthropology talks about people in groups. History occasionally talks about global structures, ourselves as member of a larger global, international, or regional community. Biology talks about the biosphere. So I hope you're seeing that to understand these embedded identities that shape each of us, we need different disciplines, because different disciplines tell us about different identities. And then there's the earth sciences. What is this planet we're part of? How does the atmosphere work? How do the oceans work? Why are the continents shaped the way they are? We need geology to ask that and to understand that. We need astronomy to understand our relationship to the sun that provides most of the energy that drives life on Earth. And then finally, we're part of a universe. So we need cosmology and physics to understand the rules of this universe. So I hope this gives you some sense of how our sense of identity is embedded in something much larger, and how connecting disciplines is really crucial to understanding this larger identity. Now, this is why I've often used Van Gogh's wonderful painting, Starry Night over the Rhone. It's a great icon for what I call big history. So this is very crude, but I hope it'll give you a sense of it. It's also a beautiful painting. So there's astronomy and a cosmology up at the top of the painting. Down here, well, there's a rock or two, so let's call that geology. Over here, we've got water. That's where life began. So water is a wonderful container for chemistry and biology and for the origins of life. Over here, we have buildings. So we've got anthropology and history. We've got cities, churches, and human civilization. We've also got electric light. So we've got modern history. We've got the modern world somewhere. And the missing bit is... This is not a test, but how many of you have figured out what the missing bit is? The missing bit is you and me at the center of all of this, trying to figure out what is our relationship to all of this. And that is what the humanities disciplines try to do in many ways. So that's why I love this painting. You put them all together and you get a modern origin story, a modern science-based origin story, one not based on traditional texts or just mere authority, but based on modern science. Now, so let's think about the idea of building a modern origin story. So if I persuaded you that we need a modern origin story, how do you go about building it? Well, all I can do is describe my own experience. And there's a shameless plug for my recent book here, Origin Story. It came out last year, and it's a summary of the history of the universe. That's the Penguin edition. I'm going to plug the Swedish edition in a minute. So, teaching a modern science-based origin story is a project that's been with us since the Enlightenment, from when science first began to emerge. And one of the central ideas of the Enlightenment is we need new knowledge that will liberate us and allow us to build a better world. And that new knowledge will be scientific. Can we provide a whole system? This is what the encyclopedia tried to do, that's based on modern science. So big history tries to tell that story as we understand it today. The story of everything, from the Big Bang to the creation of Earth, the creation of stars, the evolution of life on Earth, the history of our strange species, Homo sapiens, and to today's world, in which one species, our own, is taking over the planet. So, here's the Swedish version of my book. These are the only two plugs, I promise you, in the whole talk. In the late 19th century, the Enlightenment project of trying to build a modern origin story quite suddenly seemed to be abandoned. Now, it's a very strange passage in modern intellectual history, but I think it's a really profoundly important one because it shapes the intellectual world we lived in. And it was abandoned, I think, for two reasons. First, because the science was not good enough in the 19th century to really assemble a large and powerful story. So attempts to do that in the 19th century by people like Comte or Marx were saturated with ideology because there were so many gaps that needed to be filled in. And the second reason why people gave up on this project in the late 19th century is, I think, the tsunami of modern knowledge that emerged with science. There was so much new information. No one knew how to deal with it. So what happened was that we entered a fragmented world of disciplines. Teaching, research, scholarship of all kinds was broken up into disciplines. And this worked extremely well. Within the disciplines in the 20th century, a fantastic amount of new knowledge was accumulated. But there was a price to be paid. And the price was we lost the unified vision. The idea of putting it all together, because it just seemed too difficult and too complex. I think now the science is good enough that we can return to that project, and that's really what big history tries to do. We need the wide-angle lens of big history in order to understand where we are today. So big history is returning to that Enlightenment project of trying to construct a modern, science-based origin story. So how do you put it together? Well, this is my attempt. I'm a historian, so I guess I tell stories. And so what I thought when I first thought we should try a history of everything was I thought, well, I'll invite cosmologists, astronomers, geologists, planetary scientists, biologists, anthropologists, ancient historians, and get them all to give lectures. And let's see if it all just fits together and magically a modern story appears. Well, in fact, this is me storytelling in Tianjin in China in 2014. We invited lecturers from all different departments at Macquarie University in Sydney. They gave wonderful, fantastic lectures, and God bless them. I spent a lot of time phoning people up saying, I'd phone up someone in the astronomy department and say, look, I'm teaching this course on the history of everything. Would you mind coming over and giving a quick lecture summarizing your entire discipline in 1 hour for my history students? And so I got used to people dropping the phone in the background and saying, oh, thank you very much, but I don't think so. But then a few people agreed, and God bless them. They were wonderful. But it was very interesting. The first year, the story didn't gel because each lecturer used their own discipline, their own jargon, their own ways of thinking, and my students were quite baffled. And at first I thought, maybe this means there is no origin story. But then something quite magical happened. Over the next few years, I listened to all of the lectures. And gradually, it was like being in an old-fashioned darkroom where you put a sheet of paper into the chemicals and you see a picture slowly emerge. Gradually, a picture emerged. And I realized there is a story, there is a unifying story to be told within modern science. And that's the story I've been teaching for many years. And now I'd like to try to give you a very quick taster of that story. This is the history of the universe in about 15 minutes. Okay, so let's go. First, the story, like any good story, has a plot. Now, the plot of the story, as I tell it, and I imagine you can find other plots in it too, is that complexity has increased over 13.8 billion years. The world we live in is fantastically complex, but that complexity is built up stage by stage. So here's a way of thinking of it. The very early universe was very, very simple. Just after the Big Bang, 13.8 billion years ago, think of a thin mist of hydrogen and helium atoms. No gold, no iron, no sulfur, no copper, just hydrogen and helium. Photons of light, dark matter, we call it dark matter because we don't understand it. Dark energy, we call it dark energy because we don't understand it. We know there was a lot of that stuff. So this sort of thin mist. There were no structures. We know a lot of this, by the way, because we can measure temperature variations in the cosmic background radiation. So we know there was hardly any difference in different parts of the universe. There were no galaxies and stars, there were no planets, there were no heavier chemical elements, no living things, there were certainly no iPhones. So this very simple early universe. And then over 13.8 billion years, step by step, more complex things appear. And that's basically the story. And it's very much about us, because it tells us how the bits and pieces of our world were constructed. Now, we need to be clear, most of the universe today is incredibly simple. If I could pick you up and hurl you at random somewhere in the universe, so you'd appear randomly somewhere in the universe, the odds are that place would be cold, it would be dark, there'd be nothing in it, and you wouldn't last for long. Most of the universe is still very simple. It does not provide environments for complexity. But over time, as the universe evolved, it began creating new environments, and environments in which more complex things could appear. In pockets. The early Earth is a beautiful example. It was a beautiful place for rich chemistry, and that's why life appeared there. So Goldilocks conditions appeared in particular places in the universe, and that's where you get complexity. And in those environments, already existing things could combine in new ways to form entirely new things that had never existed before, things with new emergent properties, such as life. So this is the story, and we look at these moments when new things appeared, and this is how today's world was built up, this fantastically complex world we live in, step by step, over 13.8 billion years. Now, the story, you'll be glad to know, has a villain. The villain is entropy. Actually, an astrophysicist I know in Australia called Charlie Lineweaver, when I said entropy is the villain, said, no, entropy is the hero. And he may be right, but just for the moment, physicists in the room, please forgive me, I'm going to go with the idea of entropy as the villain because it's much more fun. So entropy is the second law of thermodynamics. Entropy is the tendency of everything to get less organized, to get simpler, to get messier. You think of your bedroom when you're a teenager. You didn't clean it, it got messier and messier and messier. And that's entropy. And this is so fundamental that there's a kind of paradox here. There's a puzzle. Because the universe, we think, ought to be getting simpler. And in the remote future, it will get messier and messier. It'll have less and less structure. So I hope you see the puzzle. How is it possible to create complex things like you and me and the world we live in such a universe where entropy rules? Well, it's a profound puzzle. I think it's one of the most profound puzzles in physics today, and I'm not sure there's a perfect answer. So what I'm going to do is just float the answer that makes some sense to me as a historian, not as a practicing cosmologist. There are two answers, and they're linked. The first is that in the Big Bang itself, within a split second of the Big Bang, this moment when from nothing something appeared incredibly dense, containing everything in today's universe, and that thing is expanding at a huge rate, and it's incredibly hot, and it's slowly cooling. Well, actually cooling very fast at first. But rules appeared within a split second, and they said things like, there will be a force called gravity, and gravity will pull everything together. So we can identify a number of rules, and those rules guarantee that the universe would not be complete sludge. there would be structures of some kind. So here's the first reason why complex things could appear. And the second is that complex things depend on flows of energy. If you stop eating, all the complexity that is you is going to vanish within a few days. So all complex things depend on flows of energy. And in fact, those flows of energy ensure that energy itself will dissipate and become messier and less organized over time. So I hope you see that entropy, in a perverse sort of way, loves complexity, because complexity is doing entropy's work. Think of the waste that a city like Copenhagen generates. This is a fantastically complex entity. It's doing entropy's work. It's creating waste. So, the universe was capable of more complex things. Now, I want to look at a timeline. And let me try and explain one or two things about this timeline, and this is going to take us through the whole history of the universe. Over here, I've got events. And 8 of those events, and here are the first 4, I call thresholds. These are moments when something utterly new appeared. Now, of course, I could have had 1,000 thresholds. I could have had just 2. But 8 is about right for a storyteller, and I think they are crucial chapters in our story. So the first is the Big Bang itself. It gave us a universe, and it gave us some rules. The second is the creation of stars. A universe with stars, we'll see, is already much more complex, and stars drive a lot of complexity. The third is the creation of new elements. Now, they were forged by dying stars. So I hope you can see how each step builds on the preceding ones. And then the fourth is the creation in a world that now has lots of elements. So it's got chemistry, it can have rocks, it can have water, it can have ice, of things like planets and moons and asteroids, which are much more complex than stars. So there are the first 4 steps. Now over here I've got approximate absolute dates for the first time this happened. And over here what I've done is I've divided all the dates by 1 billion. Now there's a very good reason for this. We humans are not designed to understand 1 million years or 1 billion years. Natural selection didn't do that because we won't live that long. We don't need that ability. So we really struggle to understand 13 billion years or 1 billion years. It can help by dividing all the dates by 1 billion. So let's imagine the universe began 13 years and 8 months ago. And what I'll do is I'll give you some of these dates divided by 1 billion. And you'll find it's easier to see the sense of proportion in all of this. So, let me give you an example of a threshold, what I mean by a threshold, these turning points at which something new and more complex with new emergent properties emerge. And I'll talk about the second one, star formation. Each time a new threshold happens, we'll see new energy flows. And it's really crucial to hang on to that idea, the energy flows that drove increasing complexity. So, star formation. How does it work? Well, the early universe, let's go back to that early universe, that thin mist of hydrogen and helium atoms, not very promising material for a complex world. So how do you begin to get complexity in such an environment? Well, the crucial actor here is gravity. Remember, gravity pulls everything together. So what gravity started doing was taking these gazillions of atoms of hydrogen and helium and clumping them. So the universe slowly breaks into clumps of hydrogen and helium atoms. And then gravity pulls each clump tighter and tighter together, makes it denser and denser and denser. And atoms start colliding together, and eventually they break up into their components, protons and electrons, and the whole thing heats up, and you eventually reach a temperature so high that protons start to fuse together. Now, when protons fuse, they release a huge amount of energy because some of their mass is turned into energy. And this is what happens in a hydrogen bomb. So you can think of a star as a sort of massive hydrogen bomb that keeps exploding for several billion years. So within probably, it could be within 500 million years of the Big Bang, stars start lighting up all over the universe. And I hope you can see that, here's what I was just talking about. that a universe with stars and galaxies is already much more interesting, much more complex than that thin mist of hydrogen and helium atoms. You've got flows of energy from the stars, you've got differences in density, you've got differences in gravity, you've got a much more interesting environment. And stars themselves turn out to be the drivers of the next threshold of complexity, creating new elements. Now, I'm not going to go through all the other elements. I do that in my courses and I do that in books, but I hope that gives you a sense of what I mean by thresholds, these moments when something new appears. So, let's carry on with this timeline. Threshold 5 is life. Now, life is a completely new form of complexity, and I'm not sure that anyone really has a grip on the best way of describing what makes life different, but I think we have to think of living things as being active in a way that non-living things aren't. They try to do things, or they give the appearance of trying to do things, and basically they're trying to do two things. They're trying to survive as long as possible in a constantly changing environment, and they're trying to reproduce. And the reproduction means that the patterns for those living things will survive and change over billions of years. And that's the key to evolution. So that's life. And here are some of the other crucial events. Life appears about 3.8 billion years ago on Earth. That's 3 years, 9 months ago on this time scale. The first large organisms appear only 600 million years ago. That's just 7 months ago. Now, I hope you'll get a sense of the value of this timeline if you think where you were 7 months ago. That's when multicelled organisms appeared. And then some other dates. Here's a crucial one. An asteroid wipes out the dinosaurs about 65, 66 million years ago. That's crucial for us. Because if the asteroid had not landed on Earth, if it had been 5 minutes earlier or 5 minutes later, it would have missed the Earth, the dinosaurs would still rule, and you and I would not be here. So this is the fundamental stage in our story. And then humans appear. About 200,000 years ago, about an hour ago, something like that, 100 minutes ago. Then threshold 7 is agriculture. Now here's a question. Does the appearance of our species really deserve to be described as a threshold in the history of the universe? Many people have said to me, David, you're being a bit anthropocentric. And my answer to that one answer is I suspect most of the audience for this story is going to be humans. So they're interested in, I'd love a few aliens to hear it, but they'll be interested in the story of humans. But there's a second and more objective answer, which is that I'm going to make the case that the appearance of our species is a very, very big deal in this story. It deserves to count as a threshold. So we entered the story just 100 minutes ago. And that's more parts of the story, and I'm not going to go through all of them. Farming is crucial because it generates new flows of energy that generate new forms of complexity. And then the fossil fuels revolution begins, that's threshold 8, just 6 seconds ago on that last timetable. Okay, part 3. How do we humans fit into this story? And why do we need to fit ourselves into this story? Well, we're very, very recent. Here's one more timeline, and it shows all these dates in that final column. The Earth would have existed for 5 years, large organisms for 7 months, our own species for 50 minutes to 100 minutes, agricultural societies for 5 minutes, the entire recorded history of civilization for 3 minutes, in modern industrial societies for 6 seconds. So again, I hope you've got a sense of the shape of the story here and how recent we are, which makes our impact on the environment so much more spectacular. So, what is it about us? Is it possible that this story can help us understand what makes humans different? And I think it is. So let me have a go at it. What changed? I've used the phrase collective learning to describe what makes us so different. So let me try and explain what I mean by this. There are many species that can exchange, that can learn. In fact, all living things seem to learn about their environments. Some species can communicate some of what they've learned. Chimps can do this, dogs can do this, crows can do this. But it's as if there's a limit to how much they can communicate. They can communicate very simple ideas such as, look out, there's an eagle threatening to eat you. They can communicate very simple ideas, but the flow of information is so limited that ideas don't accumulate across generations. We humans seem to have crossed, and I'll use the word threshold again, a threshold in the efficiency with which we exchange information. Now, imagine if I had to stop using words in this lecture and I had to do the rest of the lecture in mime. I wouldn't get very far. I hope that gives you some sense of how powerful words are, because each word contains a volume of references and ideas. So words are fantastically powerful. Now, what this means is that we humans can share information with a precision and a volume that no other species has achieved in 4 billion years. And that's absolutely critical, because information for living organisms is power. If you know about your environment, you can control it. You can control the energy and resources in your environment. You become more powerful. And what happens is that humans share information, and that information accumulates from generation to generation. No other species does that. And so our power accumulates, our power over the environment from generation to generation. And that, I think, is what makes us so different and so powerful, and from the point of view of other species, of course, so dangerous. Now let's look, so here's now a sort of 2-minute history of humanity to follow on from this. This process of collective learning began in the Paleolithic. Here are chimps. They're normal creatures in that they evolve with certain gifts and they stay within that environment because they cannot generate the information needed to live in other environments. Humans appear perhaps 200,000 years ago, somewhere probably in East Africa, and then we watch the record and we see them starting to spread. As community by community, they're sharing information, they're learning new ideas about their surroundings. And we watch them spreading within Africa. Then by about 100,000 years ago, some of them start leaving Africa. Now look at this crossing here to Australia. This interests me because I live in Sydney. They had to have boats, they had to have navigational skills, and when they arrive, they encounter utterly new plants and animals. They have to be able to learn very quickly, and collective learning helps them. Look at this. This is humans in Siberia during the Ice Ages. Now, just try to imagine yourself in Siberia during the Ice Ages. Could you, if someone said, you say, I'm hungry, and they say, well, kill a mammoth, you know. There's a lot of knowledge there, and a lot of new knowledge. And then they spread 15,000 years ago into the Americas. And I hope you can see that each of those migrations requires new knowledge. So by 10,000 years ago, humans have spread to all parts of the world, and that means that collectively, humans have an immense amount of knowledge about all these different environments. That's collective learning at work. And it also means they control a lot of resources and energy. So there are new energy flows associated with this increasing in information. Threshold 7, agriculture. Why is it so fundamental? It's an energy grab by humans. And this is how it works. So let's go back to the sun. Fusion reactions in the sun's core generate energy. Energy pours into space. It's gathered, or some of it is gathered by plants through photosynthesis on the Earth's surface. And then what do farmers do? Well, farmers transform their environment. They divert rivers, they cut down trees, they plow the land, they plant seeds. And what's the point of all of this effort? Because it's very hard work. Well, the point is simple. You remove species that you can't use, such as rats or wolves or cockroaches, and you increase the production of those species you can use, such as rice or wheat or maize or cattle or goats. And the end result is that one species, our own, is getting more and more of the flows of energy that pass through the biosphere. So agriculture is a sort of energy grab by humans. And using that energy, human populations multiply. You get villages, you get towns, you get cities, you get civilizations, you get states, all the things that historians like to write about. You get more people, which means more collective learning, which means information accumulates faster and faster and faster. And most of what historians do is driven by this increase in energy from agriculture. Then by about 1800, some scholars, such as Adam Smith, are beginning to argue we're running out of energy. Things are going to slow down. We're farming all the land on Earth that can be farmed, so growth will cease. But of course it didn't happen. And the reason it didn't happen was because we found a new source of energy, a massive source of energy, and that of course was fossil fuels. Now, to get some sense of how huge this is, one way is to think of agriculture as distributing energy from the sun that was captured over the last year or two. If you burn a piece of wood, maybe this was energy captured 20 or 30 years ago. But fossil fuels are energy captured by sunlight and buried over 300 million years. This is a staggering store of energy, and we learn how to tap it and use it in the 18th century by building the first steam engines, and since then the number of uses has multiplied as modern science has multiplied. So that's the energy available under the agrarian regime from agriculture. Here is the energy that's become available as a result of fossil fuels. That line is my lifetime in there. Now, can you imagine modern society without that energy? So I hope you can see how this modern global civilization we live in depends crucially on this vast increase in energy from fossil fuels. And we now manage such huge flows of energy that we're competing with the great natural systems, the carbon cycle, the water cycle, even geological systems. We become a force for planetary change as a result of this. Now, how do we think about the world we live in? This is the Anthropocene. Many people, and I'm sure many of you are familiar with this idea, are saying we've entered a new geological epoch, the epoch in which one species, our own, dominates change in the biosphere. That's the Anthropocene. How do we think about this? Because it's good and it's dangerous. So this is very simple, but a helpful way is to think about a good and bad Anthropocene. And here's the good Anthropocene. I suspect that everyone in this room is a beneficiary of the good Anthropocene. We benefit from these vast flows of energy. Our lives, statistically speaking, will be longer, healthier, and better in many ways than those of most people who lived before us. That's the benefit of this. This graph shows the increase in energy available per person. I've seen calculations that suggest that this increase in energy per person is the equivalent of each one of us having about 100 slaves working for us in our lives. Okay? Think of the cars we drive. Think that the gas you put in is like a sort of slave. Here's life expectancy. Let's go back. Here's life expectancy. In the 20th century, life expectancy almost tripled around the world after almost 200,000 years when life expectancy was probably something like 25 to 30 people. And a lot of that was babies dying young. So this is the good Anthropocene. Most people in this room are beneficiaries. We do very well from the good Anthropocene. The bad Anthropocene is the fact that these energy flows are so huge that they're disrupting the normal functioning, or the way the biosphere has functioned over the last few million years. Here's a graph of carbon dioxide emissions, and I hope you'll agree, it sort of parallels the graph of energy. This, again, is my lifetime. Now, carbon dioxide, as you all know, is a greenhouse gas. More carbon dioxide means warmer climates. So we're beginning to mess with the climate system, and we're messing with the oceans. Here's a graph that shows carbon dioxide emissions over 800,000 years. And I don't know if you know how these work. They dig these ice cores in Greenland and the Antarctic, and every year ice traps bubbles of air. So you can analyze the composition of the atmosphere year by year. And they can now do it over 800,000 years. And using other proxies, they can go back millions of years. But this is just 800,000 years. So there's carbon dioxide levels. This is during the ice ages, right? There's when humans appear on that graph. And here's the Industrial Revolution. And here's today. So that's what the fossil fuels revolution has done to carbon dioxide emissions. Here's a graph showing temperature trends for the past 65 million years. That's the 1961 to 1990 global mean temperature. And here are projections over here for where we're going. And I hope you can see that these worst scenarios take us to temperatures we've not seen for maybe 20 million years. That's a very, very different world from the one we're used to. So these are the dangers of the system. Suddenly, we humans are so powerful that what we do in the next 50 years will determine the future of the biosphere and all the other billions of other species that we share the biosphere with. For the first time in 4 billion years, a single species is effectively, whether it likes it or not, managing planet Earth, managing the biosphere. Changes in the last 100 years approach the speed of the asteroid impact that wiped out the dinosaur. They're not quite as quick as that destructive event, but this is very, very fast, what's happening here. Let me give, if there are any doubters in this room, and I rather doubt that there are doubters in this room, but if there are, let me give just 3 other measures of our power. Impact on the biosphere systems. We're transforming the global climate system, the temperature of the oceans, the circulation of carbon and nitrogen. And I read recently, geologists in the room may correct me on this, but we are affecting the wobble of the Earth on its axis. And the way this works is that Iceland, the melting above all of the Greenland ice sheet, is redistributing mass over the surface of the Earth. So like a top, it's now wobbling in slightly different ways, and we humans are causing part of that wobble. So that's one measure of our power. Here's a second, and it's one we all know. In 1800, the most powerful weapon humans had was probably a cannon, the sort of weapons used in the Battle of Waterloo. In the last century, we've developed weapons which, if used, could seriously degrade the entire biosphere in just 24 hours. They could do what that asteroid did to the dinosaurs. They're sitting there. Several hundred of them are on hair trigger alert, which means they can be released in 15 minutes. We often forget about them, but that is a measure of our power. We have the power, if we're foolish enough, to degrade the biosphere. And finally, our impact on other species. I read a wonderful recent article which summarizes all we know about the changing biomass of other types of organisms. And here's the real payoff. Our species has probably reduced the biomass of the biosphere by 50% in the last 50,000 years. And the main reason is deforestation, because most of biomass on planet Earth is made up by large plants and trees. So, I have a nightmare. I often have this nightmare. Is that telling me 5 minutes? Fine. Thank you. 5 minutes will do it. Here's my nightmare. I'm in a Boeing 747. Someone wakes me up in my dream and says, "Captain, we're approaching LAX. Are you ready to land?" And I look at the screens. I look at all these screens. There are levers, there are buttons. And I stare at them and I think, I haven't a clue. I don't know which lever what dial should I be? I don't know. We've built this colossal machine. We need to figure out very quickly how to land it. And that's my terror. We have this colossal power, but we don't really know how to use it. So that's the challenge we all face. So big history today. There are now lots of resources for teaching big history. As I hope is obvious, I think people need to know this story just to understand what's going on today. There are 2 free online syllabi, the Big History Project and the much newer one, Big History School. Big history is being taught in a lot of schools, mainly in the US and Australia. There are probably now thousands of students who are learning this story in special courses, and there are now lots of books on big history. So big history is making its way. It's a known quantity now. Here's Big History School, which Macquarie University just released a few months ago. It's still in a kind of very early version. Why does all of this matter? Well, these are my grandchildren. That's my son Joshua. The cool one with the glasses is Evie Rose, who's just had her 4th birthday. That's Daniel, who's 9. They are going to be managing a planet in 30, 40 years, they and their generation. We need to help them. We need to give them the information and perspective that they will need to manage an entire planet. This has never happened before. That's the challenge that faces them. And I think big history will need to be part of their education. And it's because of them that this really matters. Because if we get it wrong, their lives are not very good. If we get it right, their lives can be as good as ours, maybe better. So I thank you very much for your attention. I did it. Thank you very much.